In this problem, we take two speakers and we are facing them at one another, and we are playing the same frequency, but the catch here is that they are out of phase. They're actually 180 degrees out of phase, and I'd like to show you what that looks like. Let's say that we have a wave that looks like this. To be in phase would look something like this. This would be 0 degrees out of phase, which means if you look, the peaks, and I just drew this, but the peaks are matched up and they are completely in phase with one another. To make them 180 degrees out of phase would look something like this. This would cause total destructive interference. 360 degrees would be matching up again like this for the most part. Again, I just drew it freehand, so forgive me. So again, 0 degrees, 180 degrees, and 360 degrees. So we're at 180 degrees right off the bat, which means that we can actually, the question is basically how far apart, what is the minimum distance that we can place these speakers such that they will constructively interfere and destructively interfere. And because I told you that they're already out of phase, meaning they are looking like this and they're going to cancel each other out, that means that we can actually just put them right on top of each other with a distance of 0, and that will give us a total destructive interference. And so the answer to that one would just be 0 meters for that. So that's kind of the first part of that question. That's the easier answer, just because, again, we know that they're out of phase already. So since they're out of phase, if we just play them on top of each other, they're going to destroy each other and cancel each other out. But because we also are asked to figure out if they constructively interfere, we need to go a little bit further. Now, if they're in phase, there's kind of a rule. We know it's not in phase, but if they were in phase, you would get constructive interference if the distances between them are any multiple of a wavelength, right? So to show you a visual of that, right now they're in phase, right? If I have a distance and they're a wavelength apart, then they're going to just look like that, or that, or that, and they're going to add on top of each other. But if they're half a wavelength off, if the distance is half a wavelength or multiples of a half wavelength off, then they're going to create destructive interference. So that's kind of just a rule here. So destructive is n multiples of a half of a wavelength. But that's if they're in phase. We were told that they're 180 degrees out of phase. So what that means is we actually just switch these. So it'll be destructive when it's n multiples of a half, and it'll be constructive when it is it'll be destructive when it's multiples of a wavelength, and it'll be constructive when it's n multiples of a half a wavelength. So that what that means is we have to put them a distance such that they are n halves of a wavelength away. Now the minimum would just be this being 1, because if it was 0, then that would just cancel it out and that would not be an answer. So the lowest integer that we could put there is 1. So the distance would equal 1 times the wavelength divided by 2. But we don't know what the wavelength is. We know what the frequency is. So what we can do then is we can use the frequency and the wave speed equation to figure out what the answer is. So I'm going to rewrite this down here. The frequency is 305 hertz, and the wave speed equation says that the speed of a wave is equal to the frequency times the wavelength. We want the wavelength, so if I solve for that, I divide both sides by frequency and I get this, speed divided by frequency. The speed of a wave in air given to you in the textbook is 343 meters per second. So that's 343 divided by the frequency, which is 305. And so we get, when we put that in the calculator, we get 1.125 meters. Excuse my one there. And that is the total wavelength. But we just went up here and we said that this is going to be our distance, our minimum distance of separation. So then we can plug the wavelength in there. So it's going to be 1 times the wavelength of 1.125, and that's divided by 2. So we're basically just dividing that wavelength by 2, and we get a distance of 0.562 meters. We were given 3 sig figs, so we'll leave that in 3 sig figs. So 0.562 meters. And 0 was the other answer.